So, hello everyone. Just a second. So, yeah, excuse me. Just a sec. Uh, So, welcome to today's live interactive session on geology and soil mechanics. So, today is our ninth week of discussion session, as you all know, and we have covered almost 2 months of our discussions and the course, and the two-thirds of the course is already over, and we are just remaining with 1 more month of discussion and course, right? So today we'll be having the ninth, then 10th, 11th, 12th. With the 12th discussion session, we'll be ending the course, and then after that, we'll be having one more 13th discussion session. That will be the revision session. That will be 1 hour long revision session where we will just discuss everything from the first to the end. Okay. So apart from that, we are almost done with the course. Just 1/3 of it is remaining, and in those the 1/3, we have some important topics that we have to discuss. And one of the topics that we are discussing is the topic of shear strength, and we discussed that in the previous session too. And we will be continuing with that in today's session itself. Okay, so let us start. Sorry. So let us start with today's session. So similar to the other sessions, we will be just having a quick recap of whatever was taught in the ninth week, and then we will just proceed with solving the problems. The problems will be simple, straightforward, so we can easily solve it, right? So let us start. So we have discussed about this CD test, right, in the previous class, right? We discussed about the CD test. So in CD test, what happens? So in triaxial test, you have two stages. First is our consolidation stage, and the second stage is our drainage stage, right? Consolidation stage and the drainage stage. No, drainage stage, the shedding stage. Okay, the consolidation stage and the shedding stage. So in consolidation state, what we do in CD test, we apply the cell pressure, we apply the confining pressure or cell pressure, and then we allow the soil or the soil sample to consolidate under that particular cell pressure, right? We allow the soil to consolidate. After consolidation is over, after consolidation is complete, what we do? We start the shedding stage. In shedding stage, as it is a drain test, we open the drainage valve and we slowly apply the deviatric stress. Okay, slowly increase the deviatric stress or the axial load, and we start the shearing of the sample. We do that very slowly so that the rate of strain is so low that excess pore water pressures do not develop into the sample. So we drain the sample and we drain the sample, and in the meantime we also uh, apply the deviatric stress. So that is our CD test. And CD test, if you remember, you get the effective values only because the pore water pressure is zero. This pore water pressure is zero. Sorry. So we get the effective stress parameters. All right. So now there is something called the Scampton pore pressure parameter. So there are two parameters A and B. So first we are discussing about the parameter B. So what is B? B is the so if you can recall the CD test, what happens? The in the consolidation stage, first what you do, you first of all what you have to do, first you have to apply the confining pressure. Okay, confining pressure, and first before you start the consolidation process, you have to ensure that the soil is 100% saturated, right? So consolidation, how do we define consolidation? Consolidation is defined on saturated soils, right? So 100% saturated soils. So you need to ensure that our sample is 100% saturated. That our sample is 100% saturated. So what you do when you apply the when you apply the confining stress, what happens? As the soil is saturated, there will be a increase in the pore water pressure too. Okay, as you increase the confining stress, there will be a increase in pore water pressure too. So now this capital pore pressure parameter P is nothing but the increasing ratio of the increasing pore water pressure, excess pore water pressure divided by the application of the applied confining stress. Okay, the ratio of the excess pore water pressure divided by the confining stress. Okay, the sigma 3. Okay, that's the minor principal stress. If the soil, when the soil becomes, so what you need to do, you need to keep on checking it. So you increase the confining stress, you check that is the how much is the pore water pressure increasing. So you can measure the pore water pressure. So there are pore water pressure transducers in the system in the setup. So that actually measures the increasing pore water pressure. So if you apply the sigma 3, you will see how much, you will check how much the use increasing. So now for completely saturated soil, what will happen? Whatever confining stress we increase confining stress we apply, that same amount of increase in pore water pressure will be coming, right? So if the soil is 100% saturated, so the B is approximately equal to 1 for saturated soil. Okay. Okay, subsoil, but for in practical purposes, it is seen that for steep soil the B can be little less than 1. So generally what we do ensure that the B parameter is about 0.95. Okay, more than 0.9, about 0.95. We ensure that the P parameter is about 0.95. Okay, before we start the consolidation process, we ensure that the B parameter value is coming approximately 0.95. Okay, so this ensures that the sample is saturated. Okay, so what is the B parameter? Finally, B parameter is nothing but the ratio of the increased pore water pressure divided by the applied confining stress. Okay. Yeah, right. So we are defining this B parameter now in CD test only, because as I said, in the in the shearing stage, our drainage valves are open and we shear the sample so slow that the pore water pressures do not develop. So this B parameter is only related to the first stage. Okay, the consolidation stage of the test. Okay. Now there is one more parameter, the A parameter. So the A parameter, let us see what is the A parameter. So we define this in terms of the CU test. In case of the CU test. So what is the CU test? When CU test, in the second stage, what you do? In the second stage, the drainage valve is closed and you don't allow the drainage to occur. So when we apply the levatric load into the soil, what will happen? The excess pore water pressure will increase even in the second stage. Okay, when you apply the increased levatric stress, the pore water pressure is going to increase in the soil because the drainage is not allowed, not allowing drainage of pore water in the second stage. This is a shearing stage. So in the shearing stage also, when we apply the levatric stress, the pore water pressure is going to increase. So in that case, this A parameter is actually defined for the second stage of the trajectory test. So, so you can see we have defined parameter A bar. A bar is equal to what? Delta UD by delta sigma T. So pore water pressure increases by delta UD on increase in levatric stress delta sigma T in the second stage. Okay. So why is CU test sometimes preferred over CD test? So CU test is generally sometimes preferred over CD test because CU test is faster than CD test. So CD test is quite slow. Okay, CD test is quite slow because when you are sharing the sample in the second stage, you need to do it very slowly so that excess water pressures do not develop. But in CU test, the second stage can be a little bit faster. Okay, that's why you generally sometimes prefer CU test over the CD test. And also in CU test, you can both get the total stress parameter, also the effective stress parameters. Also, you can get similar to the CD test. You can also get effective stress parameters from the CU test. Okay, so uh, see, this was the test, right? So you get one more circle. Okay, now this is the total value. Now, if the soil is a normally consolidated soil, then the pore water pressures will be negative. So the effective values, effective mode circle will be something like this. Okay, so from this circle you can get a total stress value, and from this circle you can get a effective stress value. So both effective and total undrained values you can get from the sieve test. Okay, undrained parameters, both effective parameters and both the total stress parameters you can get from the sieve test. Now, okay, see, now let us see. Now, at failure, AF is equal to A. I mean, at failure, the value of F. Okay, equal to at failure by failure. Okay, U at failure by sigma D at failure. That's fine. For a normally consolidated clay, the uh, AF, at failure, the parameter A bar varies from 0.5 to 1, and for over consolidated clay, the A parameter varies from minus 0.5 to 0. Now you can see for normally consolidated clay, the A parameter is positive, and for over consolidated clay, the A parameter is negative. That is because uh, if I plot the pore water pressure, so it is negative, you put positive here, and here you have the strain. Okay. Now when we have a normally consolidated clay sample or a loose sand, for normally consolidated clay sample, the behavior is something like this. But for over consolidated clay or dense sand, what happened? The behavior is something like this. So there is some dilation. Okay, dilation. That's why what happens? We have negative pore water pressures that develop. Okay, negative pore water pressure. So this was for what? This is for normally consolidated. So we can minus. So what is effective? Effective is total minus pore water pressure, right? So this is positive. So then we will get circle something like this. But if the there is dilation in the soil sample, what will happen? There are tendency, if there is a tendency of dilation in the soil sample, then you will be having negative pore water pressures. Then the effective values will be what? Effective values will be actually higher than the total stress values. So for these particular sample, this is for over consolidated, this is for normally consolidated. So over consolidated, you have negative values of pore water pressure because there is a tendency for the soil to dilate. So you have a negative pore water pressure. But for normally consolidated clays, we have a positive pore water pressure because there is the soil reduces in volume during consolidation. If you give chance for the soil to consolidate, it will reduce in volume. Okay, that's why a positive pore water pressure develops. Okay. So that's why normally consolidated your phi dash, this is the effective parameter is always phi value is always greater than the total phi value. Okay, but in over consolidated it's the opposite. So there are many things. So I understand that it's difficult to grasp everything at the first instant because it's very new to you, right? We are studying it for so many years, so it's like very easy for us to understand. But for you, studying this for the first time, I understand that it's a little bit difficult because this shear strength topic is very vast. So we are just touching the main topics just a bit so that you can know that this thing exists. Okay. So that's why I suggest that you please go through, you read some books until you read yourself the things, read yourself and then think, introspect, the things won't get clear. Okay, hence I suggest that you please go through it, go through the stuff yourself. Okay. Just a second. Yeah. Okay, in CG test, we always get the effective parameters. Okay. Okay. Now let us see the UU test. So UU was an unconsolidated undrained test. Okay. So we don't have consolidation in the first stage, and in the second stage also we do not allow the drainage to happen. So it is a very fast test. So first what you do, we apply the confining stress. We apply the confining stress, and after application of the confining stress, we start shedding of the sample. Okay, in both the stages, the drainage valve is closed. Now, what is the increase in pore water pressure? The total increasing pore water pressure is nothing but U is equal to UC plus delta UD. So the UC is due to the application of sigma 3. Okay, so application of sigma, as we apply sigma 3, there will be some increase in pore water pressure. That is your UC. And delta UD is the increasing pore water pressure due to application of delta sigma D. Okay, so the total pore water pressure increase is nothing but UC plus delta UD. Now UC is equal to B times sigma 3. So you already know UC by sigma 3 is nothing but B. And delta UD is A bar into delta sigma 3. We already discussed this thing. So total U can be now written as B into sigma 3 plus A bar delta sigma D. Right? So we are just you are just substituting UC and delta UD by B sigma 3 plus A bar into delta sigma T. Okay. Now what is sigma T? Sigma T is nothing but sigma 1 minus sigma 3. You already know that also. That one. So you're just writing in that form. Okay. So can you tell me how were the Moore circles for a UU test, if you can recall? How was it? So for the UU test, the Moore circles were like this, right? So all were the same diameter. It all are the same diameter, so we get straight line. So you get always phi is equal to 0. Okay. Now next you have the UCS test. UCS test is what? UCS test is what? Similar to UU test, but now my confining stress is 0. So as my confining stress is 0, my sigma 3 is 0. We get something like this. So from here, what is my, so this is what? This is called my C undrained. Okay. And this is sigma 1. So what is this one? This is sigma 1 by 2. So this sigma 3 is equal to 0. This is sigma 1, which can be also known as the QU. Okay. the unconfined compressive strain. So my Cu is nothing but sigma 1 by 2, which is nothing but Qu by 2. Okay, so for purely clay soils, then phi, so phi is 0. So I will have C nothing but shear strength is nothing but Q by 2. Okay. Just give me a second. We will discuss this in a bit. Okay. Just a second. I'll just so what? Just yeah. So what do you mean by stress path? So stress path is the locus of the points representing the stress states during the progress of a test. The locus of the points representing the stress state during the progress of a test. So say when you're doing a triaxial test, so maybe CUCD, whatever, so maybe say CU test. So the first stage you have consolidated the soil. Okay, so now your sigma 3 is fixed. And in the second stage, what you are doing, you are applying, increasing the deviatric stress. Okay, you are increasing the deviatric stress. So if I want to draw the progress of the test, how will it be? So my sigma 3 is fixed. So first I increase the deviatric stress a bit. So say I will get this circle. Then I increase more the deviatric stress. So say I will get this circle. I will keep on increasing the deviatric stress, keep on increasing till I get the failure deviatric stress. Okay, this is the deviatric stress at failure. Okay, like this. So this series of more circles show what? Show the progress of the test, the progress of our test. Okay, now if I join all these points, these points will give me nothing but the stress path of our test. Okay, stress path of our test. Okay, stress path of our test. Now, a Q prime P prime plot is generally used for this stress path. So what is Q prime, P prime and Q prime? So you can see. So this P prime and Q prime are nothing but is represent the coordinates of the top of the Mohr circle. So if we have a Mohr circle, this is sigma 3, this is sigma 1, right? So top means this point. So what is this? This is from here to here, not from here, from the axis. From here to here. It's what? Sigma 1 plus sigma 3 by 2. And what is this? This is nothing but the, so this is my, this is nothing but my sigma 1 minus sigma 3 by 2. So this represent the coordinate of this point. Okay, these points. Okay, these points. Okay. So P prime is equal to sigma 1 prime plus sigma 3 prime by 2. And Q prime is sigma 1 prime minus sigma 3 prime by 2. So P prime, Q prime. Okay. Now let us see example. So CD test for a normally consolidated clay. So let us see. So for first stage, my deviating stress is 0. So then what we then we apply the confining stress and we isotropically consolidate. So consolidate. So now whatever consolidation we are speaking about it now, everything was isotropically consolidated only. Okay, we did not discuss about other processes of consolidation. So isotropically consolidated means all in all the principal directions you are applying all the directions you are applying the same stress and then consolidating the soil under that stress, that is the isotropically consolidated. Now anisotropically consolidated will mean that, say, in this direction you're applying some stress and the vertical direction you're applying some other stress. In that stress arrangement you are consolidating, so that will be anisotropically consolidated. Okay, so there are practical situations where a soil element or a rock element can be in an anisotropic condition, means in all the three directions it can have different stresses, right? So in that case, if you do anisotropic consolidation, that will be more accurate representation. Okay, so we can have more isotropically consolidated or we can do anisotropic. So generally we discuss when we speak about consolidation in this stage of our study, in this level of our study, we mean isotropically consolidated. Okay. Isotropically consolidated means consolidated under the confining stress, equal confining stress. Okay. Okay. You understand, right? Okay. So as I said, so in the CD test for NCL, in the first stage, the deviating stress is 0. Okay, my deviating stress is 0. And my sigma 3 prime is equal to sigma 1 prime is equal to sigma 3 in the first stage. Okay. In the first stage, the consolidation stage, my sigma 3 is equal to sigma 1 is equal to sigma 3 because isotropically consolidated. Hence, my P prime will be what? Sigma 3, and my Q prime will be what? 0. This will be 0. So this is nothing but initially in the first stage, that is the point I. Where is my I? So this is my I point. Okay, I point at the start of the stage test. Okay, where P is sigma 3 and Q is 0. So if I plot in the PQ chart, I will get this point. Now at any time, okay, now at any random time, at some other time during the shearing stage, what will happen? We are applying the deviating stress. So what will be my sigma 1 prime, sigma 3 prime plus delta sigma d. Delta sigma 3 is the increase in the deviating stress. Okay, which will be equal to sigma 3 plus delta sigma d. Because this is a CD test, there is no question of poor water pressure, so effective and total value are same. So sigma 1 prime is equal to sigma 3 plus delta sigma d. Now sigma 3 prime is sigma d. So what will be P? P prime will be sigma 3 plus delta sigma d plus 2, and Q will be delta sigma d by 2. Right? So it is nothing but sigma 1 plus sigma 3. Sigma 1 prime plus sigma 3 prime by 2 and sigma 1 prime minus sigma 3 prime by 2. It will be my P and Q. So this with that I get my P and Q values. So I get my P and Q values. Now if I want to plot that, it will be somewhere here, say somewhere here, say. Now gradually if you keep on increasing the delta sigma d, so we will get a path like this. Okay, we will get these following points. Okay, we'll get the following points, and finally this is the point where the soil fails. The final D point is where the soil fails, and ID will be called as the stress path. Okay, so ID is nothing but the stress path. Now for normally consolidated clays, this ID stress path, the inclination of the stress path is 45 degree. Okay, so if you find out the slope from here, you will see that the inclination is nothing but 45 degree. Okay, the inclination is 45 degree. Okay. Now, right? Okay. Now, for the same soil, if we start the eye from here, initially confining stress, you keep it here, then you will see that you are getting some something line, maybe something like this. Okay. So all these lines will be, if we join these particular points, which I am marking now, you will get a kind of failure envelope. This is known as the modified failure envelope. Okay, this modified failure envelope or the KF line. Okay, if we join the failure points in the stress path, all the failure points, if we join the failure points in the stress path, a series of tests. Okay, failure points in the stress path of the soil, same soil sample. For a series of tests, you will see that you will get a line. If you join that, you will get a line. That line is called the modified failure envelope or the KF line. So the KF line exists in our P prime Q prime space. Okay. Now, if in this P prime Q prime space, if you want to over that, if you want to plot the uh, tau sigma space, that is the Mohr circle space. You can also draw the Mohr circles. Okay, so here the Mohr circles are also drawn. So with that, you can see that this is the actual failure envelope. Okay, OF, and OF dash is nothing but the modified failure envelope that we get from the stress path. Now, if the inclination of the modified failure envelope is alpha, okay, from alpha we can actually get the phi value also. Phi also. Okay, from alpha you can get the phi value. Okay, so we'll see. Let us see here. So in tau sigma space, OF is nothing but tau is equal to sigma prime tan phi dash, right? So this is the Mohr, this is from the Mohr circle space that you're getting. Now in the Q prime P prime space, in the Q prime P prime space, that is the stress path space, OF is nothing but Q prime is equal to P prime tan alpha, equation of our KF line. So this is the equation of the failure envelope, and this is the equation of the modified failure envelope. Okay, there is nothing but the KF line. So if you know the slope of the KF line alpha, you can get the, you can relate it to the slope of the failure envelope, that is the nothing but the phi, nothing but a friction. You can get it like this. Okay, so rather than when you do a test, when you do the triaxial test, after you do the triaxial test, rather than drawing the more circle, it is always easier to find the P dash, P prime and Q prime points and then plot it and get a line, right? Rather than drawing circle, you can just get a easily, you can, it is much easier than drawing circles and then drawing a common tangent, right? You just get the P prime, Q prime points and you just plot it, you get a straight line, you take the slope of the straight line, you get alpha, and from alpha you can get the phi prime. Okay, rather than drawing the circles and then getting the common tangent, measuring the slope, what you can do, you can plot it in the P prime Q prime space. You draw the line, you get the slope, from the slope you get the phi prime. Okay, that is much easier. Okay. Just a second. Yeah. So we saw for the the CD test. Now let us see for the CU test. So CU test, in CU test, the second stage was undrained. Okay, the second stage is undrained. Okay, not drained. So here the second stage is undrained. That is the excess pore water pressures will develop. And for the normally consolidated, our excess pore water pressures are positive. Right, so positive excess pore water pressures are going to develop. Okay, that will in the CU test for normally consolidated clay. So if for CU test for normally consolidated clay, so let us see how this. Okay, so let us see how our stress path is going to look like. So in the first stage, similarly, we'll have only sigma 3 that is present, right? Sigma 3 is present in the first stage. Okay, only sigma 3 is present. So by P is P prime is sigma 3 and Q prime is obviously 0. So I get the I point. Okay. The stage 2, you apply some deviatric stress. You apply some deviatric stress. So what will be my sigma 1? Sigma 1 is sigma 3 plus delta sigma D. Now what is sigma 1 prime? Sigma 1 prime is sigma 3 plus delta sigma D minus the pore water pressure. So minus delta UT. So my sigma 3 is nothing but, similarly sigma 3 prime is nothing but sigma 3 minus delta UT. So my P, from this I get some P prime value and I get some Q prime value. Now if I plot this, you will get this point U prime. Okay. Similarly, if you increase the deviatric stress, you will get U double prime, and then finally at the failure point, you will get the point U. So the stress path, here's the stress path now for a CU test. For a CU test is, the stress path now for a CU test is nothing but a curved line. So if I start my stress from here, I will get a curved line like this. Okay, this is for the CU test. If I plot the effective values. Now, instead of the effective values, if I want to plot the total stress values, that is PQ, instead of P prime Q prime, if I want to plot the PQ values, I will get, obviously again I will get a line like this. So this is my total, this is my effective. And from here to here, this difference is nothing but delta UT. Okay, this is for the uh, CU test. Now, for a CD test, if I plot the effective values for a CD test, if I plot the effective values in CD test, there is no total, there is always effective, right? So for a CD test again, if I plot, this is for my CU test, not this, it will be curved. P prime. So remember now I'm drawing for the effective values only. So for this is for what? This is for CU test. Okay. Now for CD test, if I plot in the plot the effective stress path, I will get like this. Again, this is for CD. So both are effective here. Okay, because prime. Okay, remember prime. We are putting P prime and Q prime. Okay, for CD test, you will get something like this. Okay, because there is no pore water pressure, excess pore water pressure. So for CD test, you will get something like this. So yeah, so as I said, so P prime Q prime, so CU test for NC clay, and this is for the CD test for normally consolidated clay. Now for over consolidated clay, the picture will be something different. So I am not showing it here, not to just not to confuse you. I am not showing you because in over consolidated clay, first you have some positive pore water pressure that develops, and then that pore water pressure becomes negative, right? So hence I am not discussing that. Okay, I am not discussing that. Okay. Stress path concept is very important for understanding critical state soil mechanics. So there is a topic in soil mechanics called as the critical state soil mechanics. Okay, which is a quite advanced topic. Generally, we study it in masters. Okay, during our masters, not in the bachelor's. So, not in the undergrad. So, in critical state soil mechanics, to understand the concept, concept of stress path is very important. So, everything there is explained with the help of stress path. Okay. Okay, so now let us see this. Okay, so Scampton pore water pressure parameter we studied, right? A and B parameter. Okay, so A and B parameters, what is the relation between this A parameter and B parameter and how we get them? So let us see that. Okay, let's see that. And just a second, I'll just discuss a bit. Uh, just a second. So yeah, so just Campton portrait ratio is as we're discussing. So delta V by V change in volume times the stress. Okay, the change in volume by the applied stress, the mean stress. Okay, by the mean stress that you are writing. Delta V by V divided by delta sigma 1 plus delta sigma by 3 means change in volume by the mean stress is equal to 3 times 1 minus twice me by E, which is nothing but equal to the compressibility of the soil skeleton. Okay, so this is the constant. That is delta V, then we can write as CV times this particular quantity, where we convert the effective stress, all the effective values, the total value. So hence we get a pore water pressure uh, value here. Okay. Also, delta V is equal to the change in the volume of volume of water delta VW, nothing but N into VCW into delta U. So hence we can write it like this, and then after that we have delta U is equal to 1 by 1 plus N CW by CV into delta sigma 3 plus delta sigma 1 minus delta sigma 3 by 3. So this is for the conventional triaxial test, as I said, isotopic triaxial test where delta sigma 2 is equal to delta sigma 3. Okay, and you are increasing the sigma 1 only. Now delta U is then can be written as B times delta sigma 3 plus A times delta sigma 1 minus delta sigma 3. Now delta U1 is nothing but this first term B times delta sigma 3, and delta U2 is nothing but the second term AB into delta sigma 1 minus delta sigma 3. So AB can be written as A bar, nothing but delta sigma 1 minus delta into delta sigma 3. A bar times delta sigma 1 minus delta sigma 3 is delta U2. A total change in water pressure is nothing but delta U1 plus delta U2. Now A bar, if you see, A bar is nothing but A into B. So we had discussed about A bar, right, previously. So A bar is nothing but A into B. And if B is equal to 1, if B is equal to 1, then A bar and A are both are same. Okay. Now, for a completely saturated soil, the water fills the pore space. Right? The pore space will be filled by water. Okay, pore space will be filled by water. So CW will is and CW is much less than CV. Okay, CV is the compressibility of the soil, and CW is the compressibility of the CV is the compressibility of the void space, and CW is the, I think, the compressibility of the water. Okay, so CW by CV is going to be equal to 0 because CV is much larger than CW. Okay, so B is going to be 1. Now for dry soil, air fills pore space. Okay, air fills pore space. So my CW is much larger than CV. So hence this will be infinity. So in that case, my B is equal to 0. Okay, so if we have water in the pore space, so you know that water is considered kind of incompressible, right? Incompressible. So my CV, that is the compressibility of soil skeleton, that will be much higher than the CW. So in that case, my B becomes 1. Now for dry soil, the CW is nothing but in CW there is no water, right? In the pore space we have only air. So if air is infinitely compressible, or CV is very small compared to CW in that case, so that time we have B is equal to 0. Okay, B is equal to 0. Now B can be measured in U test in the first stage, as I discussed in the initial slide itself. So B is nothing but delta U1 by delta sigma 3. For completely saturated sample, B is equal to 1. That is A bar is equal to AB is equal to A. That case. Now, what is A bar? A bar is nothing but delta U2 by delta sigma 1 minus delta sigma 3. Now, yet in the second state is in the CU where sigma 3 is a constant. For fully saturated, A equal to A bar. So, delta U2 is equal to sigma 1 minus sigma 3 is equal to delta U by sigma 1 minus sigma 3. Okay. So, we'll solve some problems regarding that time we'll get okay. Okay. So let us start. Mm, just start solving the problems. So in UCS test was conducted on a soft clay in both in situ and remolded samples. The following data were observed. Okay, so in situ, so UCS stage, unconfined compressive strength was conducted on a soft clay. So in both in situ soil samples, means undisturbed soil sample and the remolded sample. Okay, so these are the results that were obtained for both in situ sample and remolded sample. Determine the unconfined compressive strength of the soil in both conditions. Also determine the sensitivity of the soil sample. So the length of sample is given, initial area, extension of spring at failure, spring constant, axial deformation. So first you need to find out the failure load. Yeah. So failure load for in situ sample is what? 20 mm extension of spring. So 20 times spring constant. This thing but 300. This is for in situ sample. And for remolded sample, it's 15 times 15 the remolded sample. Okay, so you get the failure load. Now for the in situ failure load is 300 Newton. Correct area at failure, corrected area L is mm square. Okay, not meter square, square square. square. Okay, this is the corrected area. So Q unconfined compressive strength is 300 by square remolded. Okay, this is what the incident. Now for remolded soil sample failure load is the corrected area. Okay. Actual deformation is 20 mm for remolded sample. And so now, can you recall how was sensitivity defined? This is from the first index properties chapter. Okay, how was sensitivity defined? Sensitivity is defined as the UCS of undisturbed by remolded. Okay, undisturbed by remolded. So undisturbed by Q remolded. But there is a sensitivity is low. So if the sensitivity is generally between 1 and 2, we call it low sensitivity. Okay, low sensitive soil. Okay, done. Let us see. A vein 100 mm in dia. So this is a problem related to the vein shear test. So what is a vein shear test? If you recall, what is a vein shear test? So in vein shear test, what we do, we input generally it's done in situ. Okay, we have laboratory vein shear test also, but generally vein shear test is done very softly in the field to get the in situ undisturbed UCS value. So what you do, you vein means something like it has blades. Okay, blades like fan. Okay, that it has blades, and this is long and it has blades. So insert it into the soil and then you turn it. Okay, turn the vein into the soil. Okay, and then you measure the torque that is required for that vein to turn. Okay, from that you relate that to the your UCS values. Okay, UCS values or the shear strength value. Okay, the shear strength value. So a vein 100 mm in dia and 200 mm in height was pressed into a soft clay in a borehole. The torque was applied and gradually increased to 100 Newton meter when failure took place. Determine the undrained shear strength. Okay. So this is the relation. Chile is the undrained shear strength to the torque and the other height and other parameters of the wind shear apparatus. Okay, so this one is the 100 shear strength. Okay. So a similar problem again. So try to do this. Try to do this by yourself for a minute. Same. That's the same thing you have to use, and then you have to find out the sensitivity. Okay, just try to do. This is the same thing. Same thing. Just try for a bit, and I will solve it for you. So in in situ wind shear test on a saturated clay, a torque of 43 Newton meters was required to shear the soil. The dia of the wind shear 61 and 100 determined the under shear strength. The wind was rotated rapidly to cause revolting of the soil. The torque required to shear the soil in the molded state was 8 Newton meters. Determine the sensitivity of the clay. So SUTS 100 shear strength. This okay. This is 100 shear strength. Okay, and S demolded sensitivity and 2. Same, simple. Okay, let's see this. An embankment 5 meter high is made up of soil whose effective stress parameters are C is equal to C prime is equal to 50 kPa and pi prime is equal to 16 degrees. And the unit weight is 16.2 kilonewton per meter cube. The pore pressure parameters are as found from triaxial tests are A is equal to 0.4 and B is equal to 0.49. Find the shear strength of the soil, the base of the embankment, just after the soil has been raised from 5 meter to 8 meter. Assume that the dissipation of pore pressure during the stage of construction is negligible and that the lateral pressure at any point is 1/2 of the vertical pressure. So you're raising the height of the embankment from 5 meters to 8 meters. In that, during that construction stage, there will be some excess pore water pressure that develops. And considering that, you need to find out the shear strength of the soil. Okay, so yeah. So what is my shear strength nothing but sigma plus C plus prime 10 prime. Okay. Now, what is my total pore water pressure increase? Okay. Now, what is delta sigma 1? Increase in vertical stress now. My embankment was something like this, say, it's 5 meters, then it was raised by 3 more meters to make it 8 meters. Okay, so increase in vertical stress is increase 3 times the unit weight. We have to calculate at the base, the shear strength. Okay, 6 kPa now sigma 3 increase in lateral stress. Sigma 3 will be nothing but the increase in lateral stress. Lateral stress is half of the vertical pressure. So half of the increase in the vertical is nothing but 24.3 kPa. Now delta U is what? B times sigma 3. So what is B? So B is given. B is given in the question 0.49. So B into bracket delta sigma 3. What is my delta sigma 3? 24.3 plus A. A is given as 0.4. So I put 0.4 times delta sigma 1 minus delta sigma 3. So what is the increase in delta sigma 1? 48.6 minus the increase in sigma 3, 0.3. Right? So from here I get the increasing water pressure is 16.67 kPa. Alright. Okay. Now what is my normal stress? Normal stress at the bottom of the embankment is 18 into gamma, that is 8 into gamma, that is 8 into 16.2. Right, that is my normal stress at the bottom of the embankment. Now what is the effective normal stress? Let me write it as bar. Is more suitable. Huh? 8 into 16.2 minus the pore water pressure, that is 16.67. This is delta U. Okay, that will give me the effective value. So this comes out as how much? Please calculate. Please calculate this. This will be yeah, 3 kPa. All right. Now I can find the shear strength. Is my C prime, that is given 50, plus I got the effective normal stress, then 5 prime is given. Still, so this comes out to calculate this. Comes out as 82.38 kPa. All right. Now there was one more problem. Maybe probably I removed it. Okay, so let's skip to problem 6. There was one more problem, probably problem 5, which I had put, but I think later I removed it due to some reason. So we'll see that later. So let us go to this. An UCS test was conducted on an undisturbed sample of clay. The sample had a dia of 37.5 mm and was 80 mm long. The load at at failure measured by proven ring was 28 Newton, and the axial deformation of the sample at failure was 13 mm. Determine the UCS and the undrained shear strength of the clay. So the results of an UCS, so UCS, we need UCS test parameters are given. The results, that the values that were extracted from the UCS test are given. From there, you need to determine the UCS and the undrained shear strength. Okay. Failure load is given as how much? 28 newtons. All right, now delta L. The increasing length, deformation or failure was 13 mm. So I can find out the strain at failure, length change 13 by 80. Okay, therefore the corrected area is how much? Pi by 4 into 37.5 square. That is my initial area, where 1 minus L. L is 13 by 80. Okay, this is my corrected area, and this comes out as how much? Please calculate. Please calculate this. Check how much you are getting. That's 1318.76 mm square. Okay, now yeah. Now you skew you. Okay. So QU is 28 by 6 is 0.0212 10 per n square 1318.76. Sorry. The QU undentured strength is nothing but QU by 2, which is 0.0212 by 2 is 0.0106 per n square. Okay. Just so let us say this in a CU test on NC clay, the sample consolidated under the stress of 200 kPa failed at an additional axial stress of 150 kPa. The pore pressure at failure was 75 kPa. Determine analytically the shear strength parameters both in terms of effective and total stresses. What are the values of the principal stress ratios? Calculate the values of A. So we'll do slowly one by one. Okay. So CU test on it and normally consolidated clay. Okay. The uh, results of a CU test on a normally consolidated clay are given. Okay. So let us do this. Okay. Step by step. Now, what is my consolidated under the stress of 200 kPa? That means my sigma 3 failure is 200 kPa. With that, my sigma 3 F effective is 200 minus the pore water pressure. The pore water pressure at failure was 75. So F suffix means failure. Okay, it's 125 kPa. Sigma 1 F is 200 plus Divatric stress, additional stress 150 is 350 kPa. So sigma 1F prime is nothing but 350 minus 75 is 275 kPa. Okay. Now next, determine electrical shear strength parameter. So C and phi need to find out, and the what are the values of principal. So principal stress ratio easily you can find out. So sigma 1 by sigma 3 at failure. This is nothing but the principal stress ratio at failure. 1.75, and similarly effective values also I can find out. Okay, so from here we can get C phi, and from here you can get C prime prime prime. Okay. Now sigma 1 is what? Sigma 3 10 square to, so NC clay. So normally consolidated clay means what? C is 0. If you recall from interactual test for normally consolidated clay, C becomes 0 because it passes to the origin. C becomes 0. Okay, got it right? So phi 1 I know, phi 3 I know, this ratio I know 1.75. I just put this ratio directly, I know already, right? 0.75. From there I can get phi. This is the total stress parameter. Similarly, what I can get? I can get the effective stress parameter too. Okay, similarly, I can get the effective stress parameter too, right? So, similarly, I can write okay. So you can see clearly phi prime is greater than phi. Okay, for concentrated NC clay. Okay, or NC soil, phi prime is effective values are always greater than the phi values because my pore water pressure is positive. Okay. Yeah. So yeah. Just one more thing, I will just once verify from the book. That- just give me 1 second. Just check the book. Okay, now let us go to the last part. What are the values of the principal? Calculate the value of AF. AF. Okay, that we need to calculate. Okay, so C is 0 for NC clay, we already know, so that is done. Phi is done. Now you need to find out this last part. Calculate the value of AF, value of pore water pressure A at failure. Okay, that we need to calculate. So let us see. A bar is right. Derivative stress. This by this. Now, if the soil is fully saturated, okay, then what is my A bar? A bar is A times P, and if it's saturated, then P is 1, then A bar is A. Okay, so mm, yeah, so I can write this A is equal to sigma 3. Now, since the first stage it's consolidated, that means I'm allowing the pore water pressure to get dissipated, right? So in my first stage in CU test, it's consolidated test, right? So since it's a consolidated test, there will be no pore water pressure in the first stage, only the second one will be there, right? So this I can write directly delta U by. But in case of UU test, okay, UU test, or if you want to initially check if the soil is consolidated, that is different. Okay, don't confuse with that. Okay, UU test you have delta U1, and in CU test also, CD test also, when you are checking initially whether it's saturated or not, that time the drainage valve is closed. Okay, while checking When you are checking that time, you were like having this U1, but when you are consolidating, after you have consolidated the sample, at the end of the consolidation stage, there is no excess pore water pressure because our pore water pressure is dissipated. Okay, that's why this E1 I'm telling is 0. At failure, so delta UF at failure 75 and delta sigma 1 minus delta sigma, the deviated stress at failure is nothing but 150. It's already given. So 0.5. If you recall, for NC clay, the AF is always between 0.5 to 1. Right, so hence you are seeing it, it's between 0.5, it's 0.5. Okay, and for our consolidated clay, it is between minus 0.5 and 0, I think. Yeah, minus 0.5 and 0. And for our consolidated clay, and for NC clays, it's between 0.5 and 1. And for our consolidated, it's minus 0.5 to 0. Okay, so let's do the next problem. The results of a series of CU tests on an undisturbed sample of an over-consolidated clay whereas below. So over-consolidated clay sample, we are doing CU test. This is over-consolidated, not normally consolidated, it's over-consolidated. Hence you are saying the pore water pressure is negative at failure. Okay, pore water pressure is initially negative. Determine the effective shear strength parameters. Plot the variation of AF with OCR if the pre-consolidation stress is 700. So we'll do this. Okay. First, let us write test number. Then we have sigma 3 at failure. Then we have sigma t at failure equal to sigma 1 at failure minus sigma 3 at failure. Then we have sigma 1 at failure to failure, sigma 3 prime at failure, and sigma 1 prime at failure. It's 4 tests, so 1, 2, so just 1, 2, 3, 4. Sigma 3 at failure is 100, 200, 400, 600. Okay, deviating stress at failure is 300, 410, 610, 850. Sigma 1 is nothing but this plus this, so 400, 610, 1010, and UF is minus 45, minus 15, 50, 110. So sigma 3 is 145, 215, 350, 490. Sigma 1F is 445, 625, 960. Okay, so we got this. Now next, what is our task to determine the effective shear stress parameter? What we need to do, we need to draw these 4 Mohr circles. Okay, we need to draw this 4 Mohr circles with the sigma 3 f prime and sigma 1 f prime. We need to draw the 4 Mohr circles and then we need to draw the common tangent to them. So if you do that, we will get the slope of the tangent will give you the effect phi prime and the intercept will give you the C prime. Now one more thing here is that we can also find the C prime and phi prime from the P prime Q prime plot. That also you can do. That option also you have. Okay, that option also you have. So if you plot the Mohr circle, you will get some Mohr circle like this. Okay, for the 4 Mohr circles you are going to get like this, and then you draw a common tangent. Okay, and which is nothing but our what failure envelope, and the slope of that is nothing but the friction angle phi prime 25 degrees, and the intercept C is nothing but a C prime. Now, what you need to do, one more thing that you need to do is that you need to do this by yourself once. You take a graph sheet and then plot these values and check whether you are getting this or not. Okay, please do this yourself. Do this exercise yourself once. Okay. Now, what is the next part? Plot the variation of AF with OCR. So, what is OCR? Over consolidation ratio. What is over consolidation ratio? Over consolidation ratio is nothing but the ratio of the initial stress by the what? By present value of stress. Okay, that gives us the over consolidation ratio. So we'll see. Okay. So we have sigma 3, we have OCR, and then you have to find out the AF. Okay. Now what is AF? AF is delta U by delta sigma D. Right? It is my AF. Sigma 3, I have OCR. So, okay. So sigma 3 will 200, 400, 600. Now what is the over consolidation ratio? What is the over consolidation ratio? Over consolidation, so pre-consolidation test is 700 kPa. Okay, 700 divided by 100, that will give me the over consolidation. 700 is the pre-consolidation, so 700 divided by 100 is 7. 700 divided by 200 is 3.5. 700 divided by 400 is 1.75, and 700 divided by 600 is 1.2. So this is my over consolidation ratio. Okay, over consolidation. How did you get 700 divided by 100? 700 divided by 200, and so on. Okay. Now, what is my AF? AF, AF, how to calculate AF? So, what is my increase in pore water pressure? And the first step is minus 45. And what is my derivative? So, minus 45 by 300. That is minus 0.15. That is going to give me the minus 45 by 300 is minus 0.15. Now next for 200, when it is 200, I have the derivative stress at failure is 410. So minus 15 by 410. Okay, minus 15 by 410. It's coming at 0.036, 037, minus 0.037. Similarly, for the third test, it will be 50 by 610. 50 by 610. So 50 by 610. This point is 0.082. Now for the last one, it will be nothing but 110 divided by 850. 110 divided by 850. So 110 divided by 850 is 0.13. Is 0.13. Okay, we got the AF value. To plot the variation of AF with OCR, so it will be a simple plot. It will be like this. So positive AF and we have negative AF. Okay, here we have OCR. So if it's 0, 2, like this up to 7. Okay, so it will be something like this. Okay, this is 0.13, say 0.13. And this is 0.5. So this is 1.5. Something understood, right? So graph will be something like this. Okay. So for normally consolidated, it varies from 0.5 5 to 1, and for over consolidated it's value from minus 0.5 to. So you can see still we have some uh positive uh, values, but it's not that much. So so let me show you. So for here, as our OCR is reducing, you are seeing that the AF pore water pressure becomes positive. So hence AF also becomes positive. But for highly over consolidated soil, with 3.57 high over consolidation ratios, we are having negative pore water pressures that are developing. Okay, we are having negative pore water pressure. Okay. Let us see this next problem. This solve very fast. A compacted soil was tested in an undrained triaxial test using a cell pressure of 400 kPa. Before the application of cell pressure, the pore water pressure in the sample was 0. So these are the value of strain, dielectric stress, and pore water pressure. Determine B. We need to check initially if the soil is completely saturated. So if B is 1 initially, that means the soil is completely saturated. Then plot dielectric stress with strain and plot A with strain. So let us do that. Let's do it. Yeah. So let us make the table. Okay, I'm just writing the change in pore water pressure. Okay, change in pore water pressures. Okay, change the first 250 minus, sorry, 285 minus 250, 150 minus 285, 105 minus 150, 75 minus the increase. Okay, the difference I am writing. The differences I am writing here. And dielectric stress is already given, just directly I am writing those values. Yeah. Now, okay. Now, first, before that, let us determine B. Determine B and check was the soil completely saturated. So, what is B? B is delta U by delta sigma 3. So, how much is the pore water pressure changing? 250. What is my delta cell pressure? 400. So, this is 0.625, which is less than 1. Okay, that means it is not completely saturated. It means not completely saturated. Okay, not completely saturated. Okay, okay. Now this ends the first stage. First stage. Now next we start applying the derivatives test. Now that's why that is come to an for this problem. Okay, the second part of the problem. Okay. Now there A bar is delta U2 by delta sigma 1 minus delta sigma 3. So delta U2, everything I have, just I have to divide and write. Okay. So B I know. Now A I can find out from A bar. A bar by B will give me my A. Okay. So quite simple only. Directly all the values are given. Just correctly you need to plot, and then you can plot your strain with respect to A. You will get something like this that you can do by yourself. Okay. That's all. Next problem, in a triaxial test, a soil sample was consolidated under a cell pressure of 700 kPa and back pressure of 350 kPa. Thereafter with drainage not allowed, the cell pressure was raised to 800 kPa, resulting in increase in pore pressure of 440. So on 700 to 800, the cell pressure was uh, raised. The pore water pressure increased from 350 to 445. The axial load was increased to give a deviator stress of 575. Cell pressure remained at 100 800 kPa and a pore pressure reading of 640. Where the pore pressure coefficient begin. Let us do. So what is B? B is delta U1 by delta sigma 3. So delta U1 will be nothing but 445 minus 350, as I said. Back pressure is nothing but the pore pressure that develops as pore water pressure. 800 minus 700. So it's 4.95. So almost equal to 1. So quite saturated, right? Now, axial load was increased to give a deviator stress of 575 kPa. Well, cell pressure. So sigma uh, 1 is what? Sigma 3 plus sigma D. Sigma 3 is 800. Sigma D is 575. Which will give me 1375 kPa is sigma 1. Sigma 3 is 800 kPa, sigma D is 575 kPa. And the pore pressure reading is also given 640. Calculate the pore water pressure coefficient BN. So what to how to calculate A bar? D, so sigma. So now pore pressure is 640, right? So see what is the increase? 640, initially it was 445. Sigma D is 575, right? 25. So this will come out as 0.339. Now A I can write by A bar by B is 0.339 by 0.95 to come out as 0.357. Okay, this is how it do. So it just take care that you are using the increase the differences, not the absolute values. You need to add a change in how much change in water pressure with how much change in temperature that you need to consider. So at pore pressure reading of 640 means reading is 640. Initially it was 445. So on 445 now it has come, the reading has come to 640. So the difference you need to take. So that you need to consider it very properly. Okay. So that's all very simple. Others it's very simple. Okay, so now let us do this. A sieve triaxial test on a saturated clay sample give the following results: cell pressure, deviation, pressure failure. Remain effective stress parameters, the mode cycle and stress point method. So it's quite simple, same. Okay, so uh, But if you add this, you will get sigma 1. Given values. Okay, at failure values. Sigma 3 prime is nothing but 150 minus 80. Similarly, all other values also. Okay, just deduct the pore water pressure. Similarly, sigma 1. P and Q. So what is P prime? Okay, PQ got, so 51. Okay, PQ got. Now, if you want to plot the mode circle, you will get the something like this. Okay, mode circle something like this. So phi C is coming as 0, and your phi prime is coming as 25.5. So obviously, it's a normally considered clear. That's why you're getting a CS 0. Okay, CS 0. Okay, so C prime is 0 and my phi prime is coming at 25.2. So do this yourself, okay, once. In a plain graph paper, you plot all the circles and try to tangent and check whether you are getting the same values or not. Okay, just do it yourself. And now if I want to draw, find it, so do it by stress point method. How will I do? I will just plot my P and Q like this, P prime, Q prime. I will get a line like this, which is my modified Fourier envelope. We'll get alpha bar. Now, this one I can get an inverse tan alpha bar. From here I can get phi. So this will come as to, we will check, you check this, okay, do this and check yourself. You'll see that it will come out as 23 degrees about, and then you can get as 25 degrees. Okay, so one more thing I will just give you, not related to this. So say you have like this, huh? This is Q prime, this is P prime. So you get a modified failure envelope like this KF line. This is my KF line. Get alpha, and you get this intercept as A. Then my C is A by cos I, and my sine is, sine inverse then alpha. Okay, so this way you can get C and phi from my modified fill-in. All right, so this was all for today. I hope you understood everything, understood the stuff that were taught to you. The problems are quite simple, plus just pay attention to the effective values, the total values, the water pressures, what you need to take. Just pay a little bit attention to that. Apart from that, everything is quite simple, and you should be able to solve the problems very easily. So what I suggest is you draw the more circles and try to solve all these problems yourselves once again, and practice as much problems you can, so that your concept gets cleared up, and you are quite ready for your exam, right? So I suggest that you solve more and more problems yourself, and try to uh, um, understand the basic concepts from those problems, try to take the graphs, the main concepts. So this topic is quite vast, so we cannot cover everything, as I said, so I'm saying again and again. So just try to understand the main quantities, or the main objective, the main uh, things, the main ideas of these concepts. Okay, let's try to just read again and again the textbooks. So this is very important. We should do self-reading. Other without self-reading, it's very difficult to understand. Just read textbooks, try to think about the concepts, and that way you will be able to get a good hold over these things. Okay, so thank you so much for attending today's session. Our next session will be next Monday, the coming Monday, that is on the 31st. the 31st of March, we'll be having our next session. And yeah, so that will be our 10th session, right? So next Monday, 31st of March, from same time 6 p.m. to 8 p.m. We'll be having our next session. Okay, so let us meet on Monday, the 31st. Thank you so much for attending. If you have any doubts, you have 2 more minutes left. You can ask me. I am here. Else you may leave. Okay, thank you so much for attending and have a great evening ahead and also a great week ahead. Okay, thank you.